In the last video, we had a discussion about constitutional isomers and stereoisomers, but we really haven't done an example of stereoisomer, have we? We'll just sit back and wait. All right, so here is an example of constitutional isomers. Just as a quick review, so if you take a look at ethanol, well, ethan, because there's two carbons, all because there's an OH group. Look, I just weaseled in another old lecture module, didn't I? CH3CH2OH, ethanol, and dimethyl ether. So these are constitutional isomers because they have the same number of carbons, they have the same number of hydrogens, and they have the same number of oxygen. They are just linked a different way. So here we have an alcohol, and here we have an ether, ROR, and they are different functional groups, folks. They're different functional groups, but they are still constitutional isomers. They are linked in a different way. Well, if we look over to the right-hand side, 1-chlorobutane and 2-chlorobutane. Okay, well, same number of carbons, same number of hydrogens. They are just connected differently. This one has the chlorine at the very end, one spot, and 1, 2, 3, 4 butane, 1-chlorobutane. And then this one has the chlorine in the second spot, 1, 2, 3, 4 butane on the second carbon. I have a chloro group. There we go, 2-chlorobutane. Down here at the bottom to the left, two more constitutional isomers, pentane and isopentane. I hope so, because we're using iso. That really represents isomer. Well, 5 carbons all in a row, or 5 carbons, same number of hydrogens. It just makes this kinky little L over here to the end. And that's my iso unit, isopentane, or 2-methylbutane. And then finally here, we've also introduced the carbonyl group, right? The carbonyl group is right there in the world of alkynes. And this carbonyl group could have been an aldehyde or it could have been a ketone. Well, if I take this, which at this point right now is a ketone, R, carbonyl, R, and I shifted the double bond O down, and I put it toward the end. Folks, it's the same number of carbons. It's the same number of hydrogens. It's the same number of oxygens. But this now is an aldehyde. So once again, two different functional groups, and that's okay, but they are still constitutional isomers. That's the world of constitutional isomer. And this is what we've been doing. We have been doing this over and over. We've been drawing these. We've been naming them. We've been getting more familiar with them. So the question that people always have is, okay, just lay it to me, right? You tell me what I'm getting ready to sign up for in the world of stereoisomer. And this is how I do it. Okay, you ready for this? Stereochemistry. In the world of stereoisomers. How difficult is this going to get? How difficult is this going to be? Because I have a feeling it's going to get more complicated, right? And I'm going to say, well, bear with me. Just be patient. Way back in the world of alkenes, carbon, double bond, carbon. Look, I'm wrapping another lecture module in. I keep weaving it. We were drawing structures that kind of look like this, right? And sometimes we'd put like a hydrogen here and a hydrogen there, and maybe a methyl group here and maybe an ethyl group here. And in the nomenclature, because we drew it this way, we did it that way on a purpose because we wanted you to tell me a little bit about the geometry around the double bond. And you would look at this and you said, oh, okay, so hydrogen here and hydrogen there, and with hydrogens, we probably use the cis and the trans form, right? Yes, that's what we used. And you would look at these two hydrogens and you said, hey, these are on the same side. So this is the cis form of that molecule. And I would say, yes, good for you, check. And I move on to the next question. You just did stereoisomer. Yeah, that's all that this is. You just did it. Because if you look at this structure, and if I redraw the structure to give you the other form, okay, well, let's keep this side the same, and let's flip this side. So the hydrogen's now on opposite sides. If you look at this molecule is not attached in a different way. This is not a constitutional isomer. I have a carbon and a carbon and a double bond and a carbon and a carbon and a carbon. And the same thing happens down here at the bottom. I've got a carbon and a carbon and a double bond and a carbon and a carbon and a carbon. The only thing I did was flip them. They are different in space. They're not different in how they're attached. Just to prove that point, let's name it. I look at this top molecule, and I need to provide a name for this top molecule. What do I give it? Okay, well, longest carbon chain. 1, 2, 3, 4, 5. 5, pent. Hopefully you can give me that. This is a pentene because there's a double bond. It's an alkene. And this is going to happen at carbon number 2. That's the closest to the end. So 2-pentene is the name of that molecule without cis and without trans added onto it, right? 2-pentene. There you go. Okay, well, let's name this one without cis and trans. What kind of name would you give me here? Longest carbon chain. 1, 2, 3, 4, 5. Pent. Okay. And this is an ene because there's a double bond. And second carbon in, there's where my double bond is at. So 2-pentene. Folks, it's the same name. Same name means it's not a constitutional isomer. Constitutional isomers required it being hooked up in a different way. And these are not. Your name proves it. The name tells me it's the same linkage. But there's still a difference. And the difference is the way they have oriented themselves in a 3D environment. These are molecules that take up space. They're molecules that have dimension to them, not just the silly little structure on a sheet of paper. And because of that, there is a difference. That double bond does not rotate. That double bond, because it does not rotate, points things in different directions. It points the hydrogen on that carbon up, and this one points the hydrogen on that carbon up. Folks, down here at the bottom, that carbon still has a hydrogen. It's still pointed up. This carbon still has a hydrogen just like up above. The linkage is the same. It just points it in a different direction. And this is where cis and trans came from. Well, E and Z are also stereoisomers. They went hand in hand. So we've already talked about this. We've already done these. Whew. Thank goodness. Wipe the sweat beads off your forehead. I mean, we went round and round and round with EZ, cis, and trans. EZ, cis, and trans. We named EZ structures. We named cis trans structures. We drew cis trans structures. We drew EZ structures. All of that is the same in this lecture module. So good news for us, the majority of the work has now been done for us. Because we've been doing it already. We just didn't know what we were doing. And maybe you really felt that way when you did that lecture module. I don't know what I'm doing, but I'll do it. Well, okay, it's coming back again. So cis and trans and E and Z, be prepared. They're going to throw these questions out once more. They're just going to reaffirm that you know what you're doing. And it really confirms to you that you know what you're doing as well. Another thing that we also did during this time, just to jog those memory cells up in your head, are ring structures, right? So we did cyclohexanes mainly. That's kind of what we did. So here's my chair cyclohexane ring. And remember there were axial and equatorial bonds. I'm just going to draw axial bonds on this one. They're easier to draw and they're easier to see. And we also said that these cyclohexane rings, we drew them over and over. We named them. There were groups on them. And let's say that a group was here and let's say a group was there. Well, this is axial. It points up. And then its neighbor automatically points down. These are in opposite directions. Opposite directions mean that this was a trans molecule. These were trans-methyl groups. Both of them on the axial position. Okay, so that's something that we did back in the day. That's also stereoisomer. They're connected in the same way. But folks, I could get them on the same side or I can get them on opposite sides. How do I get them on the same side? Okay, well, I take this methyl group that's on that carbon, and instead of putting it on that axial that goes straight down, I'll put it on an equatorial group. So equatorial here would go slightly down, and here it would go slightly up. Remember, equatorial and axial, they point in opposite directions. So if this axial goes straight up, that also has an equatorial. That equatorial goes slightly down. The same thing happens here. If this axial goes up, this axial goes down. That's just the nature of the cyclohexane ring. Well, 3D fashion, equatorial goes slightly down, equatorial goes slightly up. So I'll put the CH3 on that equatorial bond, and doing that gives me another isomer. And this was up, and this is pointed up. They're pointed in the same direction, so this would be the cis version. That again, folks, is stereochemistry. That is stereoisomer. All of that coming back. Every bit of it. So if you didn't get it the first time around, good news. We're going to be talking about it again. We're going to be maybe doing problems with them again and so forth. So just be prepared for that. Something else that they're also going to do that will be kind of new. We didn't really talk about it in detail, but it is something that we're going to focus more on. And that's this whole concept of a wedge. Okay, so what do I mean when I say a wedge? Like a doorstop wedge? No, not a doorstop wedge, but we are going to be drawing wedges on a sheet of paper. So let's say I didn't have a cyclohexane ring. What if I had instead a cyclobutane ring? I could. You know, that's a possibility. So everything is locked into place, just like a cyclohexane ring would be locked into place, just like a double bond would be locked into place. So cyclobutane would also be locked in. And there's really no good way to draw these ring structures unless it's cyclohexane from up here at the top. We have a way that we do that. But what about all these other rings that can happen? Notice we didn't ever talk about them. Notice we just kind of dropped them as an old shoe and just forgot about them. And we only paid attention to cyclohexane. Well, we don't have to. We can give these other guys a little love too. Make them feel wanted. Don't leave them out. Well, how do we do that? Well, let's say that this has a hydrogen on it. And let's say this has a chlorine on it. And then maybe in this other corner, let's draw a hydrogen. And here, let's draw maybe a bromo. I could leave it like this. And nobody would ever know anything about stereochemistry. They're just lines representing bonds that really aren't even there. They're not sticks. It's just a set of two electrons. That's all it is. Just glue to hold it all together. But I could give you an idea of stereochemistry. And here's how we do it. I'm going to look at this top left-hand carbon. It has two groups on it, a chlorine and a hydrogen. This hydrogen, I've got a line right now. I'm going to change it to a wedge. This chlorine I've got a line. I'm going to change that one to a wedge. This hydrogen down here at the bottom right hand, I'll change that one to a wedge. And the bromo group, guess what? I'll change that one to a wedge too. All right, so we're working with wedge structures now. W-E-D-G-E, wedge. So there's two different versions. There is a solid wedge that we can use, and there is a dashed wedge that we can use. And they represent different directions. Typically, solid wedges come towards you. So imagine these flat, maybe on a sheet of paper. If you see a solid wedge, they're pointed up towards your face. If you see a dashed wedge, they are typically pointed away from you. That's how we interpret these bonds. Again, 3D fashion. It kind of points away and toward the back of the paper. So as of right now, if I wanted you to name it, this is a cyclobutane, right? And then I have a bromo and a chloro. They're both halogens. One doesn't necessarily take priority over the other. Because of that, where do I really start numbering? Do I give chloro the one spot, or do I give the bromo spot the one spot? Well, B comes before C. So IUPAC rules would say typically this is going to be a 1 bromo and a 3 chloro cyclobutane. And that's how I would leave it, because you've not given me anything about stereoisomer right now. You just drew some bonds. That's all. Well, I'm getting ready to show you. How do we do this? I use wedge structures. How do I use the wedges? Solids point toward me, dashes point away. And if I take this wedge and I fill it in, let's give this one a solid wedge, and let's give the bromo a solid wedge. The bromo and the chloro group are both pointed toward me, toward my face. That's what that represents. Well, by default, these are going to be dashed wedges. The hydrogens are pointed away from me, and they both are pointed in the same direction. Oh, the hydrogens are pointed in the same direction. The bromo and the chloros pointed in the same direction. If I asked you, is this cis or is this trans? By looking at these dashed wedges, you would say, hey, the hydrogens are both dashed wedges. The hydrogens both point away from me. They both point in the same direction. So therefore, this is the cis version of 1 bromo 3 chlorocyclobutane. And I would say, yes, you are correct. That's how we interpret these. All right, well, what if we keep the same structure, but I'm going to change the 3D shape, meaning I'll put the bromo here and the hydrogen here. I changed the direction. Notice I didn't do anything different. It's not a constitutional isomer. That carbon still has a bromo and a hydrogen on it. That's no different than what it was before. The difference is the orientation. How does it point in space? Well, now I'll look at this and I say, hey, here's a test question. Is this cis or is this trans? You would look at this and you would go, oh, okay, so hydrogen is a dashed wedge. It's pointed away from me. And this hydrogen is a solid wedge, so it points toward me. One is away, one is toward. That means they are pointed in different directions. If they're pointed in different directions, doesn't that mean it's trans? And the answer is, yeah, that's exactly what that means. Folks, you've just learned your first lesson in stereochemistry. That's what this is going to be all about. Did you feel okay with that? If so, do not make this lecture module more complicated than what it should be, because this is really all there is to it. The tricky part is just being able to draw these the proper way on a sheet of paper. So for instance, if they give me a name and they say, hey Tracy, why don't you draw trans 1-bromo-3-chlorocyclobutane, I'm going to have to be able to do that comfortably on a sheet of paper. That's really the difference here. So, with that, in the next video, we're going to do some of these examples. We're going to be drawing cis and trans forms for a couple of different compounds, and now we are going to use our BFFs. And our BFFs for this lecture will be solid and dashed wedges. I now know what their purpose is. I now know when I look up these structures on something like Wikipedia, of all things, okay, yeah, I'll let it slide. Wikipedia, I use it myself. But when I see these weird bonds with these solids and dashed, I now know what those represent. They're trying to give me an idea of which direction these atoms are pointed in because maybe it's important and they want me to focus in on that part of the molecule. So in the next video, we'll do some examples. And with that said, why don't I just go ahead and show you what those examples are going to be? And it's here. So why don't you, before you hit play on the next video, write down these structures, these names. Draw the structures. Have them ready. And when you hit play on the next video, we'll go through and we'll talk through these structures to figure out if you gave me the proper structure or not. And once again, if you do this, you'll start to realize where you're messing up. And if you can pinpoint where those problems are and how to prevent those problems from happening, I think that will do you a little bit of good in the future.